Okay, Dashers. So we are starting our last unit, which will cover the next 2 weeks. And waves are so important to our everyday lives because we count on technology, medical technology, um, and obviously natural things like light and sound to communicate. So you can see a few reasons here why it would be useful to study waves. So I'm glad we're getting to study them this year too. Um, then um, we always start this unit though with physical things that you can see. Okay, so and my spring is bouncing in the background still here, but that way you have something that you are familiar with that you can imagine. And then when we get to light and sound, those waves are, things that we can graph in math. They are not things that you can see with your naked eye. Obviously, you can see light, but not as a wave. At least we can go back to these ideas though. So we start off by talking about periodic motion, which is any kind of motion that repeats. And so you can see some examples there, and play that guitar string video if you would like to see it. Okay. And then we get more specific, but so talking about forces again, going way on back to our forces chapter. If you remember, equilibrium was when the net force on something was 0. And so something is going to repeat motion if it's being pulled and pushed to get back to equilibrium. So if the net force becomes something other than 0, trying to pull it back to its equilibrium position, this is certainly the case for a guitar string, then that's what causes it to cycle through its motion like that. Okay. And then there's this very specific kind of periodic motion we're talking about today, which is called simple harmonic motion. And that's a special case when the further you pull that thing away from equilibrium, the greater the force that tries to pull it back to equilibrium. So that is a special situation. And the reason we're studying that today is because the graph of that looks like a wave, but we'll get to that in a second. So then a couple vocab words that go with this. The time to complete one cycle is called period. We studied that actually way back at the beginning of the year when we did the pendulum lab. And then amplitude, I think you've talked about that in math too, which is the maximum distance that the object moves from equilibrium. I'll show you an example in a minute. Okay, so the one of the examples of simple harmonic motion is a mass bouncing on a spring. It can bounce up and down or side to side. And the reason this works is that the math equation for the force of a spring on an object is this equation right here, where K is a certain number that stands for basically how stretchy or how difficult it is to stretch the spring. And then X stands for how far you've pulled the mass away from equilibrium from this dashed line here. Okay. So I'm gonna go to the next slide and then I'll show you my masses bouncing. Okay. So then, for example, if you graphed this bouncing, or if this oscillation back and forth, this one is like a cart that's rolling, but it's connected to a spring that's connected to the wall, and it's allowed to shake like back and forth. No matter which one you graph, you will get a sine or cosine wave. And the amplitude we were talking about is this, how far did you pull it away from where it would want to be, so to speak, where the net force is 0 right here. If you pulled it A, or if you pushed it negative A, those are the amplitude measurements we were talking about. And then the period is the time it takes to complete a full cycle. Okay. And then the only other example of simple harmonic motion is a pendulum, okay? Because the more you pull, a swing, you know. So if you remember sitting on a swing, the further you are back from the straight up and down position, the harder gravity's going to try to pull you. I mean, you almost are going to slide out of the seat, right? So that's another great example of simple harmonic motion. Okay, so I'm going to pause here and take a video of some motion. Here are two different two different springs and the same mass connected on each one. So it's a lot of white in the background, but at least you can hopefully see the springs and the masses. So now if I set the amplitude, okay, which actually doesn't affect much about the period. It doesn't affect the period at all, actually. Ooh, that's kind of wild. Okay, let's try to straighten that out a little bit. But you can see which one has the longer period, right? This one is shaking up and down, and it completes a period in a pretty short amount of time. But this spring mass system takes a longer amount of time to complete one cycle, so it has a longer period, okay? All right, so that's one example of simple harmonic motion. Let me pause and put that to the side. For a pendulum, I just chose a necklace here, an old one I found. This is pretty cute. Okay, but so the pendulum has a certain period, a certain time it takes to complete a cycle, and that, for a pendulum depends on the length here of the string. If I make this shorter, then it will have a much shorter time to complete one full cycle. Okay, if you have a big clock at home, you know the pendulum inside is made of solid material, right? But that clock works because it has a set amount of time it takes for that pendulum to swing back and forth. Okay, and then this last little bit here is talking about a really specific situation that happens when force is added to a system that's vibrating. And if you add force at just the right time, which is called the natural frequency of the system, then you can get this system to shake harder and harder and harder so that the amplitude goes up and up and up, okay? And so the best and most familiar example for most people is pumping a swing. So if you think about being on a swing right now, like that little girl in the picture, think about, when do you add force? Like, how are you adding force? Okay. Well, you're really adding force in two places or two specific times. You are doing that, you're like leaning back when you're at the farthest point back. So you're shifting your weight, okay? And then when you get to the farthest point forward, you're leaning forward, kind of accentuating that effect. And then your amplitude, that's like how far you are from equilibrium, that's the definition of amplitude, keeps on increasing. Okay, so right now that seems kind of obscure, like, why are we talking about pumping a swing? But it becomes important later when we talk about, um, if you were to study how does your radio work? Why can you tune in a particular station and only hear that station? Um, MRIs, the R stands for resonance. Okay. So those are very sophisticated topics we're not going to study in this class, but they resonance is the reason why a lot of our technology works. So okay, and then if you want to look at the next cartoon, it's kind of funny. Um, it's just about like that person who shakes their foot or or their chair. Which hey, are you that person? Because we're not usually sitting at a table with somebody right now when we're doing our schoolwork, but um, how that can drive you crazy. But then how you could play a trick on somebody if you could shake your foot right at the right frequency or at the right times so that you could spill this guy's drink. Okay, so uh I will post a video that's a nice um demo of resonance, but for now, I think that pumping the swing is the best example and the easiest one to explain. Okay, thanks for listening today, ladies.